Good afternoon, everybody. Today, I'll be discussing on analysis and design of tall structures. Tall structures means not only buildings, but also tall chimneys, tall towers. So I'll be discussing different aspects of analysis and design of tall structures. Now, let me start with my lecture. Initially, I will show you some photographs of tall buildings, chimney, etc. And then I will discuss the important aspects of analysis and design of tall structures. Basically today, I will discuss those aspects, but in my future lectures, I will elaborate those aspects regarding wind excited oscillations, effect of earthquakes, etc. Many aspects are there which are need to be discussed in detail so that you can appreciate the requirement of exact analysis or correct analysis and design according to the codes. Codes doesn't mean that only Indian code. One can consult other codes also, American code, British code, Euro code. So there are many codes are there which we can consult, but our main objective is to design a safe tall structure and at the same time, if it is a building, very tall building, then many people will be staying there. So naturally, we have to also take care of the comfortability while designing the buildings, because if the occupants are not happy in staying in those buildings because of huge sway or drift of the tall structure, then our objective is lost. So I'll come to those things one after another. Now, this is a photograph of the tallest building in the world that you all know, Burj Khalifa. Maybe some more are coming up, but officially I know about it. It is in Dubai and 828-meter high. Now, this particular tower of various activity, when they designed, just look at the photograph, that every block of the tower, they have not taken to the top. It is not a uniform tower. And some blocks are stopped at a particular level. Maybe another block which is taken to the next level. But the core of the building, that is taken up to the highest level. So this is a kind of structure, and why it is done and why it should be done. All those things, when I'll be discussing in detail, you will be able to appreciate. And that is my objective. Now you see, this is Shanghai Tower in China. It is 632 meter tall. But the architecture is a bit different. It is not a similar structure like Burj Khalifa. Now, this is done normally to achieve a safe, stable structure, obviously economic also, and whose performance under extreme wind and seismic provides a certain comfortable level of the occupants. So this is a really challenge. So it is not that for all the tall buildings the architecture will be same, the elevation will be same. No. Because with some architectural treatment, we can also reduce the effect of wind. Rather, you can say the building will be more economic. Just if we make some architectural treatment, it can be done. But only thing is that right at this moment, I will not discuss in detail about those things. But later on, I'll tell you why they have done this kind of architectural treatment and what is the benefit they got out of it. This is another tower. It is Ping and Finance Center in Shenzhen, China, 599 meters. So 200 stories. Here also the architecture is different. The elevation is different. It is not same as the structures which I have shown you before this. This is Lotte World Tower in New York. It is 541.3 meters. Again, the architecture is different. I am not going into the detail of it, that why the architecture is different, what is the advantage they got out of it. Because those things I'll be discussing in detail in my future lectures. This is Tianjin CTF Finance Center in Tianjin, China. This is also, the architecture is different. Taipei 101 in Taipei, it is 508 meters tall. Here also the architecture is different. Now you see, for every building, it is not that they made the architecture different just for architectural reason. No. It is also related to the wind effects on the structure. So don't think that they are just, changing the architecture just casually. No, it has got some other structural behavior aspects also. This is the Petronas Tower in Kuala Lumpur. Two towers are there, twin tower in Malaysia for 51.9 meter. This particular tower, more or less at the mid level, it is connected. Now, one may think that this is just done from artificial concession. No. Many buildings, many tall towers, many twin towers, they are connected at various levels. And out of that, we get some structural benefit. The structure becomes, very safe, economic, and also performance of the structure under extreme wind and earthquake is acceptable. This is Willis Tower in Chicago, USA, 442.1 meter. This is also, you see that there are several blocks, but they have stopped a particular block at a particular level, but the core block, they have taken up to the top. It has got some advantages that slowly you will understand when I will go into the deeper part of the subject. This is Marina 101 in Dubai, 425 meter high, the highest tower, because all the towers are not of same height, but they are very close to each other. And when the towers are very close to each other, and when there will be extreme wind, there may be buffeting effect, interference effect. That means one particular tower, when it vibrates, it transmits its effect to the other tower. Similarly, other tower also, when vibrates under extreme wind, transmits the effect to the tower beside it or in front of it. If the buildings are very closely spaced, then this kind of interference effect or the buffeting effect normally is to be checked, because if you don't check it, then maybe your design is unsafe. Sometimes this kind of buildings, not only this building, the buildings which I have shown you there in the previous slides, those buildings are tested under extreme wind in the wind tunnel. Now, this is Empire State Building in New York, in USA, 381 meter. This is probably, it's a very old building. You know about it, you heard about it. This is Bank of China Tower in Hong Kong, 367 meters. Just see the architecture. It is totally different. Now, obviously, there are some advantages. Some advantages of structural behavior under extreme wind or earthquake. So, we want safe, stable, economic, and comfortable for occupants. We want this kind of building. Otherwise, the acceptability of that particular structure will be less. Now, this is the Earth's headquarters at New York. Just see the elevation is totally different from the other buildings. This is the tallest building in India, which is in Mumbai, Imperial Tree. Is 392 meters tall. This is another building in Mumbai, Ritz-Carlton Hotel, which is 366 meters tall. But this building is more or less uniform along the height. This is the proposed tallest building in India, which is not yet constructed. Even the construction, so far I know, the construction has not yet started because they have not got the clearance, and it will be 442 meters. This is the tallest building in Kolkata, the 42, 268 meters high, quite tall. Now you see, when you are coming to these chimneys, RCC chimneys, see this chimney, the base diameter is 7 meters and your height is 270.3 meters. Just not a matter of joke. This is RCC chimney, just height by D ratio is quite high. And you will slowly appreciate that if the height by diameter ratio or the minimum width ratio is very high, then you have to take care of wind carefully. This is tall chimneys in other part of the world. 367.6 meter chimney in US. In Canada, 380 meters. In Russia, which is now Kazakhstan, is 419.7 meters. It's quite tall, quite tall. Now let us slowly discuss different important aspects of tall buildings. Now the design of tall building, it essentially involves conceptual design, very important, which a structural engineer and architect both or a team, they will finally decide the conceptual design. Then approximate analysis is required because you can conceive something and if you finalize and later on if you find that it is not feasible for some reason, then it is not at all acceptable in the profession. So approximate analysis is done, preliminary design and optimization, that is also done, so that the building can carry the gravity load, dead load, live load, and the lateral load, wind load, seismic load. If there is a possibility of blasting somewhere, those loads, there are many kinds of lateral loads you have to consider depending on the location. There are many other aspects also. The design criteria, basically their strength, obviously, serviceability, that is the deflection, stability, obviously, and human comfort, which I was telling you that if you construct a building structurally safe, stable, but that particular building is undergoing a huge drift, huge displacement at the top, then nobody can stay there. So there comes human comfort. Even in many situations, the displacement will not be in one direction. There is a possibility of rotational displacement also. So you have to be very careful about this particular aspect. The strength is satisfied by limiting stresses, obviously. Serviceability is satisfied by drift, I already told you. It is normally kept within H by 500 to H by 1000, depending on the situation. Stability is satisfied by sufficient factor of safety against buckling and P-delta effects. Now, this buckling, P-delta effect, I will be discussing in detail in my future lectures. Human comfort aspects. are satisfied by acceleration in the range of is 10 to 25 milli-G, where G is 981 centimeter per second square. And you see, the aim of a particular structural engineer, you or me, to arrive at suitable structural system to satisfy all these criteria. Don't think that we will not consider about human comfort. Only we will consider only strength, serviceability, and stability. No, no, that is not acceptable. Now, while designing this, steel consumption kg per, if you express in terms of kg per square meter, is a very, very important parameter. And your client will always take this parameter carefully because of the cost aspect. And this weight doesn't mean that the weight of reinforcement only. It involves the floor, this girder, braces, columns. Because suppose if the steel consumption is less, fine. But if the building weight is very high, in that case, the building will suffer from earthquake. So how can we do those things? That means we have to make it as lighter as possible from earthquake point of view. Again, if you try to do that, wind may be a problem to you. And again, if you manage wind and earthquake both, but your client is not happy because he is expecting steel consumption in the lower side. So it's a really real challenge. So what I want to tell you that whatever may be the challenges, who are doing it? People like you, people like talented people like you, who has got solid background of structural analysis, design, everything. So you can do it. And obviously, the under wind, the drift should be, controlled or should be within permissible limit. Now you see, the structural system, I told you that it should be able to carry the gravity load, lateral load. But the temperature also playing a major role. If there is a possibility of blast or impact load, that is also to be considered. If you just design a building without considering the temperature fluctuation, which is happening, maybe in India, say around 40 degrees centigrade, if you do not include in the analysis, you will find that your design is unsafe. So just think about tall buildings. If you don't consider all these aspects, then you are totally dealing with unsafe design. And you have to understand one more thing, that whatever you are proposing, don't think that your client will accept immediately. He may go for some kind of third-party checking or fourth-party checking. And then finally, when he will be convinced, then he will start constructing it or spending money on that. So the tall building which we are discussing, it involves a huge number of architects, structural engineers, and they finally, after considering all the aspects, then they decide to construct it or accept it. Don't think that 10-story, 15-story buildings are not, people are not considering properly. That is also, they are taking it seriously, and saying all these aspects, they check it. And it should be able to accommodate heating, ventilation, and air conditioning system, and fire resistance property. Material which we are using, or they may go for some coating also, which is fire resistant, improve the fire resistant property. So, you see, you have to think as a whole, not part of it. You see, if you are a good structural engineer, you are good in analysis, in design, but you don't have good idea about the material. You can't differentiate the huge difference between steel and concrete or any other material. Then you will be in trouble. You will not be successful. So you have to be also good in material. You must know. And all this ventilation, air conditioning system, that is always there. So how to take it? What should be the best way out? And under, extreme wind and earthquake, whether those things will be, will not be disturbed, or even if it disturbed, small disturbance. Okay, because if due to some extreme wind or earthquake, if everything collapses, even this air conditioning system and other things, then there are also huge costs. So you have to think about it. Don't neglect these parts. Now you see, the dynamic effect should be considered both for serviceability and safety. Try to understand the sentence. Serviceability means the maximum displacement at the top of the building, the drift. Safety means any column, beam, whatever it is, it will not collapse. But you think about a situation when the natural frequency of the structure and wind or earthquake or any other load, if they are very close to each other or coincides, there will be resonance. And resonance means the building will undergo huge displacement. Even if it is not under full wind or earthquake, and it will collapse. When you are talking about safety, then obviously resonance is very, very important. So naturally, your natural frequency of the structure in different mode. It may be, the longitudinal displacement. It may be rotational displacement. In different modes of, dynamic behavior, you have to be careful so that it should not exceed a particular limit, right, due to this motion, which will not be acceptable for the occupants, because they are the buyers. Ultimately, if they are disturbed, they will never buy it. Or even if they buy, they will sell it. So the movement of in a tall building can have a wide range of human response, from anxiety to acute nausea. This can make a building undesirable. Please think about it. When you are dealing with tall buildings, please think about it. Not only I'm not requesting you. If you don't think, your proposal will not be accepted. So this movement of buildings are commonly generated by wind, earthquake, if there is a machinery, plant, various things. Even if you know that due to some railway activity beside the building may get disturbed, vibrates. So you have to be very careful. Now, I am really addressing a very intelligent, successful engineers, because they can understand why these things are required. They can appreciate the professional requirements. Otherwise, people will not accept them as a consultant for doing this kind of challenging job. Now, this is a particular code. It's a Swedish standard. It gives you recommendations regarding serviceability in state, which I was talking to you. Maximum displacement, that may be lateral or rotational, and there are criteria. And if you go through this code, you will be able to understand that unless you satisfy this code, if this particular code is mentioned in the contract document, then your design will not be accepted. So you have to be very careful. You have to be very, very careful about this particular issue. Don't neglect it. Similarly, you try to understand the variation of human tolerance regarding vibration in a building depends on both direct and indirect effect. I'm just reading out the sentence. That will be better for you to understand. The direct effect are the frequencies, magnitude, duration, variability, form, direction of the vibration, an interval between the vibration events, or exposure of human subjects to vibration. Indirect effect are audible noise, infrasound, visual. There are many, not one. There are many. All these things you have to be very, very careful. And according to this code, there are many other codes also on this particular subject. The acceptable vibration in the building, depending on occupancy, that is to be people should accept it. Otherwise, your design has got no use and nobody will implement it. And you have to think in this way that when people are investing huge amount in this kind of project, then unless they check all these aspects, they will never spend any money. They can spend huge money for engineers, architects and all, but when they will be extremely sure about all these aspects, not only structural safety and other things, also this particular aspect, they will never give the approval of the project and start constructing it. This is the reality. Now you see, commonly used structural systems are moment resting frame, you know it, shear wall frame system, frame tube, tube in tube system, bundle tube, and many more. Not only this 5, there are many more systems which will give you some advantages, sometimes disadvantages. But if you are aware of these things, and if you know the requirement of the client, and if you have got very good understanding about wind and earthquake effects, probably your choice will be the best. Now, base isolation is not that popular in India, but flexible or sliding foundation can be used. And this base isolation can also be reduced to reduce earthquake effects. And not in India, but in US or in other countries, all these things are mechanized and computer controlled. So when earthquake comes, automatically it takes care of these things. And as a result, the effect of that earthquake on building from every aspect will be within limit. So people are also spending huge money for these base isolation systems also. Not that popular in India. Now this frame tube system, frame tube structures. For frame tube structures, the lateral resistance is given by very steep moment resisting frame that form a tube around the perimeter of the building. That means, suppose it's a big building, but along the perimeters, the columns are closely spaced, maybe within 2 to 4 meters. Then what will happen? That will act as a tube, as if in the perimeter, along the perimeter, if you construct a thick wall, it will behave like that. But you can't do that because you have to enter in the building. So if you place the columns very close, within 2 to 3 meters, so that you can enter along the periphery of the building, and maybe the column spacing may be increased inside, then it is a frame tube structure. And this tube will be able to carry huge lateral load, like again under wind or seismic. Right? And the self weight is distributed between the outer tube and the internal columns or walls. For lateral loading, the perimeter frames aligned in the load direction acts as the weight. Think about it. I'm talking about a building, right? Just a vertical cantilever, and when it is acting, when the wind and earthquake is acting on it, those lateral forces, then a particular portion will be behaving as a wave, and a particular portion will be behaving as a flange. And you all know that the wave is very much essential for shear, and flange is very much essential for carrying the moment. So you see, you have got the very basic knowledge. Only thing that you have to translate into a particular structure, right, which fulfills the different aspects of the building, its safety, its serviceability, and other aspects, right, and acceptable to the client. The tube structure is suitable both for steel and reinforced concrete buildings. And you can go up to 40 to 100 stories, no problem. Sometimes, people are debating on the use of steel and reinforced concrete. But nowadays, the concrete is so good, very high strength concrete and very high strength reinforcing bars are available. So if you design a building, purely a steel building, and the RCC building, you are not sure that which one will give you the best result, at least up to 100 story building. Of course, beyond understood building, you have to also think about structural system basically, and then material also. And then ultimately you will be able to arrive at a particular solution. Now, I can tell you from my experience that when we graduated, at that time, 3-4 story buildings were normally designed. But later on, I have designed tall structures, tall buildings. And I never face any problem. Because whatever I'm discussing, these are the basic things and which you are learning at this stage. I have learned at a particular stage, or I have learned in the industry. And this particular lecture is a recorded one. If you feel like listening to this lecture again, you can listen to it. But the only thing that that you have to be very enthusiastic. You have to take a lot of interest in the subject. You have to work hard, and within a very short time, you will be able to be a very, very successful structural engineer. Now, the frame tube system has been most significant in modern times. You will find in most of the buildings they are doing it. I'm not saying that always you should go for it, because it's very easy to construct up to a particular height. Now you see this for aesthetics, the tube structure, the enthusiasm is mixed. Means some people like it, some people don't like it. And some people like the logic of the clearly expressed structure, while others, they criticize the grid-like facade as a small window and like that. See, these are the things, those who are not engineers, they are, discussing about it. They will ask a question, but you have to answer it in a proper way, because they will definitely understand your language. You can tell them clearly from technical point of view and other aspects. The survey of this tube structure is the efficiency of the flange frame for lateral loading, wind or earthquake, which tends to suffer shear lag, with the result that the mid columns are less stressed than the corner columns, and therefore not contributing as much as they could. That means what we expect, that whether the external column or internal column, whatever is the capacity of that particular column, we should be able to utilize it to the maximum extent. If you can do that, ultimately it will be a safe, economical structure. People will accept it. And that is our objective. That should be our target. So when you are discussing about something, you should always try to understand its advantage and disadvantage. And ultimately, you have to give a safe, economical structure. See, this is a particular type of structure, which that we call this as bundle type structure. What is bundle type structure? You see, if you take this hexagon, one hexagon, right, and there is a core. This is. Don't think that this will be always circular. This may be rectangular. This may be square. It depends on you. Now they are connected. They are connected like this. Okay, like this. So this is the core tube, and these are individual tubes. And this individual tube may be a rectangular one, maybe a square one, maybe a circular one. And it consists of several columns. Don't think that it is a sheer one. It consists of several columns. So you can utilize that space also. Because the size is not very small. One can go for a diameter of say 5 meters. And people can, make a small coffee shop there. So like that, if you go for a individual tube like this, right, and a core, this core, a solid RCC wall, then if you connect it like this, right, this is just a schematic diagram, not detailed, then you are getting a particular structure, which you can say bundle type. And if you just go for this hexagonal, several hexagonal, and make a core here, that is also possible. So this is some cores here, and in addition to that, there is a core here. Probably here the solid RCC wall cannot be done, but in that case, some core tube is required here, and this kind of structure, bundle tube structure, is very, very popular in tall buildings. Now, you see, this is on plan. Now, suppose if you can take this particular part up to say 50 stories. But the central one, you can take it up to 120th story. That means which I was discussing about, showing you the photographs, that in this kind of system, a particular portion may be taken up to a particular level, another portion may be taken at a higher level, but the core will be taken up to the highest level. So these are the things we will discuss in detail. Don't worry. Now this bundle tube, if I want to really write it like this, then bundle tube structure consists of several parallel rigid planes in orthogonal direction interconnected to form a bundle tube. Right? The principle is same, I told you, for single tube, where the planes are horizontally load the direction of wave and flange, wave-flange concept. And also, if you do it this way, then the problem of shear lag, that means the stress in the internal column and the stress in the outer column are different. That you will drastically reduce. As a result, the columns are more or less evenly distributed. The stresses in columns are more or less evenly distributed, and their contribution to lateral stiffness is more significant. So you will get advantage from the load carrying point of view, stress carrying point of view of columns, and also from the displacement point of view. I have shown you hexagonal because hexagonal structure has got a lot of advantages that slowly you will understand. It doesn't mean that you can't go for square one. You can go bundle tube with square one, similar concept. You can do it. So the geometry is you can change it, but the concept is this. Okay, and in this way you can allow the columns at a higher spacing. If you do this bundle tube, then the column to column distance may be increased to some extent, and it is sometimes required because in a banquet hall or a particular space or sometime for some requirement, the client is always asking you that column space, right? Now, just as an idea about this bundle tube structure, just an idea. It is just based on some analysis done by somebody. That hexagonal unit is 60 meter width, height is supposed to 12 meter. Triangular unit is this. Slender ratio is this. In that case, shear wall will be 1.2 meters at the base level thickness, and at the upper level it may be 1.2 meter thick. Mega columns. Obviously, the column will be maybe a steel tube filled up with concrete. Concrete grade is considered 90 MPa. Slab thickness is 150 millimeter. There are 5 sky bridges at an interval of 60 meters to connect the inner core of the single units. That is done. Response factor is considered 5, and the wind speed is considered in that particular example is 30 meters per second. Gust factor they calculated 1.69. Zone factor for seismic is 0.24. Importance factor 1.1. And when they analyze it, they have not constructed, they have analyzed it. Then the maximum displacement is found within h by 600. So what I'm saying that the bundle tube can be used for different types of structure of very tall structures. Even they conceived about 1200 meters. But obviously this is not constructed. This is some exercise they did it and they got it. Because the wind speed may not be 30, maybe 50. So there may be other aspects also, plus architectural considerations are there. But what I mean to say, that with your knowledge, with your basic knowledge, you can conceive. And all these things in detail, the gust factor, this, that, which I have explained to the few students who have taken wind engineering, but I'll repeat it again, don't worry. So all these things are extremely important. Now brace frame that you have shown in the the photographs, there are different types of brace frame can be used. That may be made of steel, that may be made of concrete. And huge research is going on brace frame. And the configuration of the base frame may be different. Maybe a K-type base frame. So the base frame lateral resistance are given by diagonal members that together with beams and columns form wave of the truss where the columns acting as core. So it's a kind of truss system. So this is very efficient against wind and earthquake. Right. So it is not that if I discuss here only, it will be sufficient. You see, if we discuss only on base frame for several hours, then probably it will be extremely clear to you, right? So I'll try to do justice in my future lectures. Okay. Now you see, whenever you are talking about base frame, especially concrete or steel, the people are raising question on fabrication, construction. But if you want to get some advantage out of a base frame, then you have to also carefully construct those things, and whatever problem is coming, that you have to solve it. People are sometimes complaining that due to this, the construction cost is increasing. Anyway, those things are, definitely important, but you have to deal with different structural systems, and ultimately it will be discussed among several architects and engineers, and obviously client who is spending money, and ultimately it will be accepted. If all are trying to give their best suggestions, that is which is important. Now you see, for a 10-story building, suppose in Kolkata, you may not face any wind problem. You will find that the 10-story building in Kolkata, maybe, this dead load and plus seismic load, that combination is critical. But we are not talking about 10 stories. We are talking about 100 stories, 200 stories. Now, naturally, you have to be very careful about it, and uh, more innovations in architectural treatment so that the wind effect is reduced for tall structures. And you have to be very careful about the deflection sway, because that is a very important aspect from the occupant's point of view. And this wind load is a dynamic load. You all know the wind pressure is fluctuating with time, it's changing with time. It's a dynamic load. But you can treat the wind load as an equivalent static load. That means the dynamicity is considered, but that ultimately it is presented as a equivalent static analysis. But that is okay. But whether you can do that equivalent static analysis or you have to do the dynamic analysis, that depends on the time period. For long period of time, load may be seen equivalent static, but shorter period as dynamic. This is basically the concept. And that, when I'll be discussing in detail, you will slowly understand that why the dynamicity of the wind is important, right, when the time period is short, or for the shorter time periods. Now you see, these are the aspects are very, very important. That is slenderness ratio, is height by diameter or height by minimum width. That ratio is important. Stiffness and stiffness distribution. Stiffness of the entire building is something, and how the stiffness is distributed along the height, that is different. Or along the plan. The stiffness and stiffness distribution is important. Mass and mass distribution. At the lower level, mass may be very high, but as you are going at the upper level, the mass will be less. So, the total mass is not only important, the mass distribution is also important. Shape on plan, that I told you several times, that shape is very important from wind point of view. Shape in elevation, extremely important from wind point of view. And wind and seismic parameters. That means when you are calculating wind forces, then there are several parameters of that particular site regarding wind. Those things you have to consider carefully. Seismic is very, very important. If required, you have to go for microgelation. And then you have to select the seismic parameters. Otherwise, what will happen? That your wind assessment or seismic assessment will be wrong. So you should have much more knowledge in wind and assessing the wind and seismic parameters, which is not always possible to cover in the undergraduate, even at the postgraduate. Accuracy of analysis. You see, you are learning finite element and other things, vibration analysis and many things. Why? Because if your analysis is wrong, then whatever you are saying, whatever you are recommending, that is not reliable. So that is why the accuracy of analysis is important. Design accuracy is important. Think about it. It is not a two-story building that whatever you are doing, people will accept it. No, they will never accept it. You know, those who are involved in this kind of job in different parts of the world, even in India, they are very highly paid. Very highly paid. In a normal company, how much they are paying to a structural engineer? Maybe 50, 60,000 to a young man, or maybe 1 lakh or 1.5 lakhs. But in a really very good company who are dealing with this kind of complex things, they may even give you in the beginning $6,000 or maybe $10,000, or maybe a very good person, you know, they can even increase that. So when I was in a multinational company, I used to recruit people of different categories. Many of them are from either Europe or from US or from India, depending on their capacity, knowledge. The salary may be $5,000, maybe $10,000, even more. So I have got the experience of recruiting people of that level. That's why I'm telling you. Detailing of working drawing. Detailing of working drawing is very, very important. Not only from estimation point of view, but also from construction point of view. You have to give every detail. Every detail. Because you are earning a lot. $10,000 or even more than that. Don't think that you will be able to get that easily. Construction aspects means that in many situations you have to think about the situation when construction is going on. During the construction period, due to wind or earthquake. And you have to be very careful about it. So it is not that after construction it will be safe. During construction also it should be safe. So there are many things are there, many important aspects are there, which I am trying to tell you in this introductory lecture. Why? Because start thinking from now. And slowly, slowly you will be master in all these areas. And you will be extremely useful in the industry. And people will be they will run after you. Now you see the mode shapes. This is very important, you all know. And under wind or earthquake, you all know. I'm talking about wind. Now there are lateral displacement in both directions as well as rotational mode around the vertical axis. In many situations we are not at all caring. But there is a rotational mode. And if the frequency, fundamental frequency in against rotational mode, if it coincides with the fundamental frequency of the wind, rotational wind, then you can easily understand what will happen. So don't neglect it. When you are checking resonance, means you have to check resonance against lateral movement, rotational movement, or the frequency against lateral movement, rotational movement, all these things. Now, you see the modes being excited when a building is relatively tall and large, obviously, making wind gusts not acting simultaneously. on all part, right? Thus, will tend to offset each other. This is you have to understand. This is you have to understand. The stiffness and stiffness issue of building affects resonance frequency. Right? Remember this. Remember this. Because when I will be discussing in detail, then you will slowly find that these are the major aspects. You see, uh, if the building is steep, the resonance frequency will be relatively high, and the dynamic displacement will not significant. That you all know, because you have already you have taken probably a course on dynamics. On the other hand, if the stiffness is low, the building is flexible, and the resonance frequency will become lower. This leads to the response will depend on frequency of fluctuating wind forces. This wind has got a static component or an averaging component and a fluctuating component. So in case of flexible buildings, the fluctuating component will play a major role. And obviously, when I'll go through dust factor analysis in future, I'll show you in detail according to IS 875 Part 3, 2015. So then you'll be able to understand it. However, at frequencies at or close, natural frequency will amplify, which may cause dynamic deflection is very high. This is which I was telling. You see why I have written like that? Because many things I am telling you, and in future, maybe you will listen to this lecture several times, and then slowly, your understanding about the structure behavior will be much better. You see, the dynamic wind pressure produces sinusoidal or narrowband random vibration motion on buildings, both along and across wind direction, as well as rotation about vertical axis. This is true. When we'll discuss in detail, you will come to know. The magnitude of displacement depends on wind velocity distribution and direction, but on mass and stiffness and shape of the building. These are all important things. Some cases, the effect of across wind action are greater than along wind action. We always think about along wind action, but sometimes you will find that across wind effect is much more severe. Even though the wind load is dynamic in short, the period is short, it is often replaced by equivalent static load that I told you, but that is not correct. It depends on the period of the structure, time period of the structure, which you will be getting to dynamic analysis, right? So the dynamic response is considered when a building is relatively flexible and investigate the stress levels and accelerations that may affect the comfort of the occupants. This is very, very, very important. You don't neglect occupants. Okay, they are the buyers. Now you see, these are the few aspects. I'll not go into detail, just I'm listing out so that you start thinking right from now. That earthquake collapse pattern that you have to control by introducing shear wall or something, by making joint better. That is a different, very important step. Collapse due to unintended addition of stiffness. To do that, no, you are not doing well. Correctly. I'll show you the examples. Inadequate beam column joint strength. People are neglecting beam column joint particular strength is they're neglecting. You can't do that. Tension compression failure, you have to understand properly. Wall to roof interconnection failure. That is possible. Don't think that this is not possible. It's possible if you don't take care of carefully. Local column failure, heavy floor collapse, torsional effect. Yes, it's quite possible. Soft story collapse. Then pounding. The building may displace to a great extent and it may hit the adjacent building. So that pounding effect also there. P delta effect. If you really want to understand about the ductile behavior of the building, along with this P delta effect, right, is very, very important. Then, the collapse due to windstorm. Earthquake effect and wind effect is not same. So you have to be careful. Explosion effect, if you. And then the entire structure, the entire building structure is a redundant one. Naturally, when the failure will start from a particular point, and then the failure will extend to another node, then to another node, then to another member, then to another member. So it's a progressive collapse. So you have to understand about the progressive collapse also. Otherwise, what will happen? The building may be extremely good, but due to some mistake, you have done something, a part of the building collapsed. It happened. And there are many more other aspects. Slowly you will understand it through my future lectures. So thank you very much for your attention and taking interest in this subject. Thank you very much.